prevent the need for relying solely on silver oxide batteries within the capsule, it was decided to focus on inductive charging to provide a continuous source of power through a portable power system. Inductive charging relies upon a known and calculated alignment, which is where our surgical capsule presents an interesting challenge due to the changing capsule orientation within the stomach. In order to achieve wireless power transfer, two coils are required, one coil to create a magnetic field and the other to induce useful voltage within the capsule. This means one coil must reside on the outside of the patient and the other must be of swallowable size to reside within the patient's stomach. Working within these limited internal dimensions of 11 by 13 millimeters, different coil geometries were explored, focusing initially on a single axis. Initial power system consisting of 50 turns of 0.8 millimeter wire with a 20 centimeter radius for the primary coil on the outside of the patient in conjunction with 1,000 turns of 0.1 millimeter wire for the secondary coil transferred only 56 microwatts of power to the capsule. Reviewing this design of the primary and secondary coil to maximise power transfer called upon the theory of resonance, where the coils are capacitively tuned to operate at exactly matched frequencies. In addition to this, increasing the surface area of the secondary coil and using ferrite as the core material, a power system was implemented capable of transferring 25 milliwatts of power to the capsule. The system efficiency was calculated to be 1.75% through porcine tissue. Further investigations were performed to exploit a 3-axis coil design in order to induce voltage in any arrangement or orientation with a full diode bridge circuit capable of converting the high-frequency AC input into a useful DC output to pass on to the power harvesting subsystem.
To achieve all this, a circuit was designed in order to drive the primary coil with a large alternating current. This would ensure that the magnetic field produced was large enough to transfer sufficient power to the tiny coil that would be inside the body of the patient. The circuit consists of two parts, a sine wave generator and an amplifier. A standard function generator was used to generate the sine wave, and a circuit was designed to amplify this signal and drive the primary coil. This amplifier circuit is based on a power operational amplifier, the OPA 548 by Texas Instruments, which is capable of driving both inductive and capacitive loads. This circuit was used to provide the high output current necessary in the primary coil. This coil resonates at approximately 300 kHz using a 600 picofarad capacitor in series. Initially we used high voltage ceramic capacitors, but the high series resistance of these capacitors meant that we could only drive the coil with approximately 200 milliamps RMS. We changed these capacitors to silver microcapacitors, which had a much lower series resistance and therefore a much higher current flow of approximately 800 milliamps RMS through the primary coil. On the other side of the system, i.e. the power that goes inside the body, we needed a circuit that would convert the induced voltage on the secondary coil to a stable DC voltage that would power all the devices in the capsule. The circuit also had to be able to store the unused energy. To do this, we designed an energy harvesting circuit based around the LTC 3588-1 from Linear Technology. The circuit is capable of converting the input voltage from the coil, which will be AC, to a stable DC output that can be used to power all the microcontroller and all the devices in the capsule. In addition, the device stores the unused energy in the capacitor, so if the inductive link fails, the capsule will continue to operate for a short period of time. All this circuitry was necessary in order to wirelessly power the capsule and achieve a power transfer of 25 milliwatts with porcine tissue.